My name's Sean Parent. I'm a senior principal scientist at Adobe. I work most closely with the Photoshop team. I'm in that organization, but I run Adobe Software Technology Lab, which is a small group. There are 4 of us. And our charter is to try to look 10 years out at how do we improve software engineering practice. And we describe practice as being distinct from process. So we're not concerned with whether or not you're following an agile or some other methodology. We're concerned with what's the code that you write when you sit down at the keyboard, and how do we help you write better code? And so our process is threefold. We're looking at how do we do this by improving tooling, how do we do this by improving education, and how do we come up with new ideas to do this through research. So that's what our team does. This talk originally came about because I was having a conversation with some people, and they said, you know, whenever you write code, whatever language you're writing in, it kind of all looks the same, and how do you do that? How do you write code in JavaScript and write code in, occasionally I'll write code in Objective-C or Objective-C++ or Kotlin, and somehow it's all kind of the same. And I replied that it was all about local reasoning, and then I had to explain myself for an hour, and I thought that would be a good talk. So the original idea for this talk was local reasoning in any language, but we're going to bend that a little bit to local reasoning in C++, because to do any language would take more than the hour that I have, unfortunately. There's too many details to get hung up on in C++. Some links real quick. The reason why I'm here representing Adobe is because we have almost 300 open positions in engineering. Many of those are C++ open positions, and you can find links to that there. You can also find some links to some seminars that my team has given and some blog posts and more information. My personal vanity page is the next page. This talk is already posted there, so you can find it there in several formats. If you want to steal my information, steal my slides, that's fine with me. The artwork is copyright Adobe, so don't take the artwork, but take the content, and all the source materials there, so feel free. And then a link to hilolang.org, which got some mentions. My team is involved with the development of the Hilo language. Some of you may or may not have heard of it. It actually relates some to this talk. So check it out, and we're looking for more people to help contribute to that effort. So if we're going to do local reasoning in any language, it should be in any language. So I thought I'd put that up there. So how many people ever saw this magazine? Yeah, I knew Kate would have seen it. A few of us are old enough. This is from 1981. This is Byte Magazine, which if you've never seen a Byte Magazine, it looks like a small phone book. And if you've never seen a phone book, it's a really thick book. And so this was an issue devoted to the language Smalltalk. I hope most of you have heard of Smalltalk. Smalltalk was actually created in 1979, so this came out just a few years when Smalltalk was still a new language. Smalltalk never really took over the industry, but its ideas did. And in large part because of this one issue of Byte Magazine. Everybody read this, like cover to cover, every article in here. And this had this massive influence on the industry. And we thought that Smalltalk was going to solve the software engineering crisis. The software engineering crisis was an older term that was about the problem with trying to build large software systems, and that they would fail, right? You just couldn't construct them. And this is a UML diagram. How many people here have ever used UML? Quite a few. Okay, so this is a UML diagram of a smallish system, actually. This isn't very big, but I wanted to give you a feel for this. And the really seductive idea with object-oriented programming was that we could take a bunch of classes and we could tie them all together, building like Lego bricks, and build very complicated systems. And that's how we were going to solve the software engineering crisis. And that date, the software engineering crisis, goes all the way back to 1968. So this had been a long time that this was considered a big problem. So what happened? Well, Wikipedia lists 17 major failed software projects that total $1 billion of losses since 1980. Okay. So, and some of my favorite ones are not on here, but the most recent one, 2023. 2014 was a really bad year. Okay. Now, failed here doesn't mean that the software was built and then it crashed and the plane crashed and everybody died or anything like that. Failed is the software was either never completed at huge expense and huge investment, or it was completed but was too riddled with bugs to ever serve its purpose and then was canceled. Or in a few cases, it was so late as that by the time it shipped, it was irrelevant, right? The entire industry had moved on. So that's what a failed software project is. One of my favorites, which is actually not in these top 17 on Wikipedia, is the Denver Airport luggage control system. They were going to, when they put in the Denver airport, they were going to build this, they built a system of tunnels and switches, and they had 114 PCs, and they were all going to control the luggage, and you would put your luggage on the conveyor, and it would all get to the right plane at the right time, magic switching. And they were saving lots of money because the tunnels were not big enough to put a person through. And there are videos online of people with really long steel poles banging the luggage out of these tunnels because they jammed and because the system never worked right. And it was all a software failure. And the company who built it had built systems before that worked, but they were a much smaller scale. So, in every single case that I could find in the analysis of why these systems failed, they talk about the management failures. Okay? There are articles and books written about management failures of why these software systems failed. But software practice, available languages, libraries, tools, fundamental algorithms, and types are never mentioned. For a single one of these, and I spent a lot of time searching, I couldn't even find, without asking people involved, what language they were programmed in. Did that choice matter? I don't know. Do we have any students in the room? Not a single one. Usually there's at least some grad student in the room. If you know a grad student, there's a PhD thesis there, right? Go research that. I'm dead serious. That would make a really outstanding PhD thesis. How many people have worked on a failed software project? Kate has. I have. Lots of people. I blamed management. Kate's like, it was management's fault. And in a lot of cases, management holds a huge part of the blame. Okay? But I also think there's not enough analysis. What they were trying to do, was it even doable? Did they know the right algorithms? Okay? What was the right process? I don't think management's entirely to blame. If you had perfect management and the perfect team and the right amount of time, it isn't clear that some of these systems could have been built. So why do software projects fail? I've got a conjecture based on absolutely zero evidence. This is a really big topic. But here's a quote. The greatest limitation in writing software is our ability to understand the systems we're creating. And I think this is the fundamental point. This is where everything goes wrong. We build systems that exceed our ability to reason about them. Okay? So, how do we go about building systems that we can reason about? That's where we tie this back to the idea of local reasoning. Right? What we want to do is be able to take our big systems, break them into small enough chunks that we can reason about them locally, we can prove their correctness, we can assemble them into larger systems, we can reason about those, prove them correct, and so on to build up the larger system. So, local reasoning, what is that? It's the ability to reason about a defined unit of code and verify its correctness without understanding all the context in which it's used or the implementations upon which it relies. We're going to be concerned today with just 2 units of code, functions and classes. And the API is the key to local reasoning. Okay? Now, local reasoning is concerned with both sides of the API. So we're going to use this terminology. The client code is the code calling a function or holding on to an instance of a class. And the implementer code is the code that is the implementation of that function or class. Okay? Because we've got to be looking at this from both sides. Sometimes I'm just going to say caller and callee when I'm talking about a function, but the idea of client and implementer extends the terminology to classes. So let's start with a very simple function. Okay? Here's our declaration of it. Tell me, what does this function do? You haven't seen the implementation. What's it going to do? Side effects, probably. That would be really unfortunate, because we're talking about local reasoning. If it has side effects, we can't reason about it locally. Okay? So, either this function does nothing, or whatever it does is through side effects. We're going to make this function do nothing. Now, can we implement it? Yeah? Everybody just, you guys are so confident. This is great. Okay. Okay. What's the key here? It's the comment. That's our specification. People get very hung up about how do you specify software. Most of the time, just a single sentence fragment, and with a period that describes what the function does, is a sufficient specification. Okay? So, with that specification, and even the really bad name of f, okay, we know what this function does. It does nothing. And even if we just had the semicolon there, does nothing, f, we know with just the semicolon. We don't have to look at the implementation. Okay, so here's another function. We're going to keep the bad name for a while. Apologies to Kate. We'll fix it. Okay. This is going to return the successor of x. Okay, does this look okay? Everybody's nodding, it looks okay. What's missing? There's something missing in our specification. A precondition. What's our precondition? Yeah. We better say that, okay? And on my team, we've been having some debates about this. Do we have to say that, or is it implied by saying it's the successor of x and there's no successor of x? But the problem is with a contract is if you satisfy the preconditions, then the function has to either satisfy the postconditions or return an error. And we're not going to return an error, we're going to do UB. So we really better say that this is the precondition. Okay. Now, preconditions are an incredibly powerful thing. They mean that we get to cut out all the bad cases and blame everything on the client. Okay? This is great. Do not underestimate the power of a precondition. Before we move on, we need to talk a little bit more about function arguments. Let's make this a little more complicated. Increments the value of x by 1. Our precondition is still there. Is this okay? Did we add any additional preconditions?
Sure.
Yeah? What's a precondition?
X should refer to an object within its lifetime.
X should refer to an object within its lifetime. That's a valid precondition. Any more? No? Yeah? So both initialized and within its lifetime. You guys are good? There's one more, the one I'm actually looking for.
No concurrent write?
Yeah. No concurrent accesses. We're writing it. Nobody else better be accessing that, right? Another thread better not have access to that int. Okay? If we do, that would have been a data race. So we're going to write this really ugly precondition. No other thread of execution is accessing X during this operation. We're going to get to the lifetime issues, so I'm not ignoring those completely. But that's a really ugly thing to write on every single function. Okay. So let's come up with some general preconditions. Arguments passed to a function by non-const reference cannot be accessed by other threads during the operation, and arguments passed to a function by const reference cannot be written by another thread during the operation unless otherwise specified. And if you're doing general preconditions, you always want the unless otherwise specified because you're always going to have some function that is special and has a mutex and does magic things. And so ignore all of that. Okay. So now we can put our code back and it looks simple again. So that's pretty good. Now we wouldn't normally pass an int by reference, but I'm going to use an int here as a placeholder for your regular objects. So why do we want to do mutation at all? Okay. Mutation can be more, well, mutation directly in place as opposed to making a copy is more space efficient, and it may be more performant, and it's often simpler to reason about, right? The simpler to reason about, because people think functional programming, oh, that can be so easy. If I say you need to change the battery in your 1968 Honda Civic, and the shop says, that's no problem, we're just going to build you a brand new Honda Civic with a new battery in it that exactly matches your 72 Honda Civic, and we'll throw the old car away. That's a very difficult thing to actually reason about. How do you go about doing that? It's much easier to think about how do I just go in and I change the battery. Okay, so in many cases, mutation can be much easier to think about. And that's what we want to do. We want to be able to reason about the correctness of our functions. So let's define a couple more terms here. A transformation is a regular unary operation, right? So it takes one argument, returns a value of the same type. Changing the state of an object by applying a transformation to it defines an action on the object. So x equals f of x is an action built out of a transformation. It's also known as a functional update if you're a functional update programmer. Now there's a duality between a transformation and a corresponding action. They can be defined in terms of each other, okay? I can define an action in terms of a transformation or a transformation in terms of an action. So I can always go back and forth between the two. But one or the other of these may be more efficient, okay? And so I might want to implement them both. I might want to implement one and implement the other in terms of the first one, okay? It depends on the operation. So classically, sort is an example of something that is better to do as an action. Doing sort in place in situ is the most efficient way to do a sort. Which is odd because typically sort is built out of a partition algorithm. The most efficient way to do a partition algorithm is with a transformation. Okay. So now we can define some argument terminology. And I'm stealing the terms here from Hilo. So this is the labeling that Hilo uses for arguments. Unfortunately, C++ gets too confusing and has too many options for the way that you can pass arguments. But we're going to say let arguments, let meaning constant, like let x equals 5 would declare a constant, is a constant reference. An in-out argument just takes the thing by reference. And a sync argument is something where it's passed by an R-value reference and it's consumed. And so if that's deduced, if it's a universal reference in C++, you want to constrain it to be an R-value reference. So, which is really ugly, unfortunately, in C++. That's a partial thing there. What's missing is you also want you want t not to be deduced as a const, which is really ugly. I wish that we had a good way to just say sync, and I haven't been able to come up with a good way to do it even with concepts. So if you can come up with a way where I could just say auto sync t, I don't know of a way to do that. There's no way to get the ref on there, right? So it's just ugly in C++. Now, each of these come with their own contract. If I have a let argument, I have an implied postcondition that that argument is not modified by this function. Do not cast away const on me. If I have an in-out argument, my postcondition is that the argument may be modified. It doesn't have to be. Okay? And if I have a sync argument, the postcondition is that the argument is assumed to be consumed. Okay? Whether or not it is consumed, the caller has to assume it was. Okay. Now, picking on C++ again, C++ coroutine handles have a really nasty interface where when you're handing off the coroutine handle, it may or may not be consumed. And that's really difficult to deal with in the face of a possible exception in error handling. Now, the client from a move from argument, the client can subsequently assign to the argument or destruct it. Those are your only options. So now we can do a more complex example. We're going to give it a good name called offset. We're going to write a function that offsets the argument x by n. And we're going to write it like this. Everybody agree? It looks okay? Okay, yeah, it's good. We're going to call it like this. What does it print? Does it print 2 or 4? 4. But we said that it wasn't going to modify n. Right? But it did. So is that the problem of the function or the problem of the caller? Okay. So it's going to print 4, but we're violating our postconditions. And we don't really know who violated our contract here. Okay. To see why this is a problem, let's implement offset a little bit differently. We're going to write a loop, and we're going to increment x n times. And we're going to call it exactly the same way. What will that print? Anybody?
Formatting of your hard drive?
Yeah, it will never print. It will keep going until it invokes UB, and it will probably keep going after that. Okay? It will never terminate. We didn't change the interface. We didn't change our contract. Okay? And now we're in a situation where our code isn't even terminating. This happens in non-contrived examples. What does this code print? Anybody? You're erasing a sub 0, so every element that's a sub 0, so that's 0 from a.
So I believe that we intentionally support this because we are not allowed to not support it, and therefore it will actually give you a vector of 1, 1.
Nope.
Then I
It was a good guess. So her guess was she believes that we actually do support this. The standard committee supports this because they're not allowed not to support it. Howard Hinton has had a number of arguments about individual functions, not this function. So there are some functions where it's true, it would do the right thing, not this one. So what does this print? 1, 0. Anybody know why? What happens is the algorithm for erase there, and there's a link to Godbolt if you don't believe me, and it's not going to be the same. According to the standard, it's actually unspecified what this means. So we're going to erase the first 0 because that matches a sub 0. But now a sub 0 is a sub 1 because that's actually passed in by reference. Okay? So now we're going to erase 1s. But we've already got a 1 in the first slot. And so now we erase the following 1, and that leaves the final 0. Okay. So that's what's going to happen with that piece of code. Okay. Now, if you really want to mess with your mind, this is actually valid C++ code. What does this do? I didn't even have to say what will it print if I tried to print A, because this is what's going to happen. Okay. So the object is actually, its lifetime has begun at the point that A is declared, and so we can pass A to its own constructor. This was actually an intentional feature of C++. I learned about this in a discussion with Bjarne, who described this feature to me as an answer to how do you solve a particular problem. I was a bit horrified at the time. Because nobody expects self-initialization. Not the standard library, nobody. That's a good way to crash your app. What it's supposed to mean is it's a way that you can write your own class that leaves an object in an uninitialized state, even though you have a default constructor that would zero it. So you can have a copy constructor that detects am I being copied from self and then not initialize your members. And in C, you can actually write int A equals A, and that explicitly means don't initialize A. Okay? So, like, nobody knew that. Nobody expects self-initialization. What does that example, though, have in common with the previous example? Okay? It's a problem of aliasing. We have A appearing twice within the same function. So, our general preconditions here. We're going to extend them. Referenced objects must be within the object lifetimes. In, out, and sync arguments cannot be accessed except directly by the implementation for the duration of the call. Let arguments passed by reference cannot be mutated for the duration of the call unless otherwise specified, and that actually covers that the arguments cannot alias, okay, because then you would be modifying one and not the other. And so making this a precondition lifts that issue out to the caller, because there is, in general, no way for the function being called to check. Now, Swift has this rule. To achieve memory safety, Swift requires exclusive access to a variable in order to modify that variable. In essence, a variable cannot be accessed via a different name for the duration in which the same variable is being modified as an in-out argument or as self with a mutating method. Okay, that's from the Swift manual, and what is it? Exclusivity enforcement. So Rust has borrowing. It says mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. Okay? Now in C++, we have exactly the same rule. Okay? We just don't have the language facilities to enforce it. It is up to each and every one of you to enforce it. John McCall coined the term the law of exclusivity. And it's the realization that mutexes and exclusive access doesn't just apply to threading, it applies to every mutation within the system, and it applies to your ability to reason about it logically. If you're writing the erase algorithm, and you're trying to handle the case of, well, what if this alias is that and this alias is that? Not only can the compiler not reason about that, and so the compiler is getting very pessimistic if it can determine that things might alias, is you cannot. Okay? In the presence of aliasing, you can't reason about your code, so it's a precondition on the caller. They cannot pass you aliased arguments. Okay? So upholding it is left as an exercise to the developer. So now I want to talk a little bit about projections. We haven't talked about function results yet. So let's start our discussion of projections there. Okay. So we had this function, returns the successor of x. And we've got that. No, sorry, I should have gone back here. Is there any reason why from a function we would want to return a reference? Okay. Some form of a reference. Yeah, some nodding. It's actually very common, right? So here's an example from the standard library. I can have this vector, and I can say a.back equals 42. A.back in this case returns a reference to the last element within the vector. And then I can print it. And it's not a quiz, it prints what you would expect. There's no aliasing issues here. Okay, so when we return a reference to a part of a whole, we refer to that as a projection, right? We've got some whole object, we're returning some projection out of it. Now, projection qualifiers mirror argument qualifiers. Okay, so we have mutable projections, right, where we return something by a non-constant ref. We have constant projections, where the caller is not allowed to mutate the thing that they get back. And we have consumable projections, which are a little bit more rare, but you can return something by an R-value reference. Now, returning consumable projections, as I said, is relatively uncommon, but sometimes if you know you're dealing with a temporary object, you might want to cough up something just before you go away. And so you could have some extract function as a member function that's bound for R-value references, which is the trailing ref syntax, and coughs up some object on its way out. Okay? And mutable projections may also be consumed, or mutable projections may also be consumed from a non-temporary by explicitly using move. But in that case, it's the caller's responsibility to put things back, okay? Either to delete that element that was extracted or to assign over it, okay? So if you move the back, some element from the back of a vector, either get rid of it with pop back or assign something new into its slot. Okay, a projection is invalidated when the object they are projected from is modified other than through the projection. Okay, so in this case, if I've got a projection, P here is my projection to the 0th element of my vector array, and then I do a pushback of 1, that reference is invalidated. Okay, that P is invalidated. So the object they are projected from is modified other than through the projection, so or through another non-overlapping projection. I can have multiple projections on something, and that's okay, and I can modify things through both of those projections, and modifying one projection doesn't invalidate the other projection. Okay? I can't do it if they're overlapping. Law of exclusivity, you have to enforce that. Okay? But doing something like this, that's going to invalidate my projection. Okay? So on this side, not invalidated. Okay. The lifetime of, and the other way that a projection ends is if the lifetime of the objects they are projected from ends. Okay? So in this case, when I'm projecting out of a vector, when that vector goes away, all the projections onto that vector are invalidated. So, P is invalidated in this case right after creation, unfortunately. I think Clang Tidy actually warned on this one. None of the compilers did. So, iterator pairs, right? Begin and end iterator pairs, views, spans. Those are a way to project a collection of values out of an object. Okay, so a view or a span, that's a projection. It follows the same rules. I can have a mutable span and immutable span. Okay, they follow the same rules as reference projections about overlapping and invalidation and lifetimes. Okay, so doing this with copy, invalid, right? I've got overlapping projections. I can't do that. Okay, this is okay, not overlapping. Now, copy has a special case, right? If you're copying to the left, it's allowed for your projections to be overlapping, okay? But that's documented as a special case, right? So all of these general preconditions always come with the clause unless otherwise specified. Okay, so that's it. With that way to just think about functions, now we have a framework within, when we're writing our function, we have a set of generalized preconditions, and now we can reason about our function, and we're only dealing with the arguments, we're not dealing with global variables. We've tried to get rid of all of our side effects, And so just looking at our function, we can go through and we can think about, what does this function do? We want to write small functions, structure them well, no raw loops, follow all of my other rules, and you can work through it. But we haven't talked about objects. Okay, so let's start talking about objects, and we're going to do that looking at it through the lens through functions. So we've got this function. It takes a shared pointer to a widget P. Is this good? Is that an in-out argument? Maybe. Is it being consumed? Maybe. Is it constant? Maybe. Even if I said it was a const shared pointer, that really doesn't help to let me know whether or not it's modifying the widget. Okay? So this is incredibly context-free, and I see this all over in the code. I do not know what that signature means. I do not have enough context to know what that signature means. Okay? What's the type of the argument f here, right? Is it the shared pointer? Is it the widget? Those are two distinct things. Okay? To understand f, we need to understand the extent of p. Okay? We need to know, where does p begin and where does p end? And that includes everything else that's pointing into p. Okay? So to understand the extent of p in this case breaks local reasoning. We cannot think through this. Now, the foundation for any kind of reasoning is equational reasoning. So I want to touch on this. Equational reasoning is proving that expressions are equal by substituting equals for equals. Okay? That's the basic idea. And equational reasoning explains how code works and is a component part of any larger proof. Okay. To know if two values are equal, we need to know the extent of those two values. So equality, which we've been talking about, is an equivalent relationship, right? It's reflexive, it's symmetric, it's transitive. I hope you all know that. And equality is connected to copy. Copies must be equal but disjoint. Okay, and what I mean by disjoint is that if I'm able to modify one side, that it doesn't affect the copy of it. Okay, so copies are equal but disjoint. This, which I threw up earlier, which everybody nodded and agreed with, okay, this is an example of equational reasoning. And this formula only holds if whatever type T is here, okay, is contained, right? If that becomes a shared pointer and there's other mutations happening in the system, does that hold? I don't know. I've lost my ability to reason about that, okay? So this simple formula only holds as long as equational reasoning holds. So how do we build up larger objects then? Well, a composite object is made up of objects called its parts, right? So we have a whole and we have parts. The whole-part relationship satisfies 4 properties. Connectedness, the whole is connected to the parts. Non-circularity, the whole is not a part of its parts. Okay. Disjointedness, the whole is not connected to some other whole, right? Modifying a copy doesn't modify the original. And ownership, when the whole goes away, all the parts go away. Okay, that's the definition of a whole-part relationship. So if I have a vector of A, 0, 1, 2, 3, right? The 1, 2, 3 values in the vector are the parts of the vector, and the vector contains them. Okay, if I have a struct like this with a name and ID, okay, that holds to that relationship. I have name and ID are the parts of B. Bad name. I can just hear Kate in the back of my head. What? You could have done better. Right? So that original piece of code, I want to rewrite it as something like this. I've got some function that's modifying an instance of my widget. And in 99% of the cases, when I see shared pointers in interfaces, they could be replaced with a reference to the actual thing that they're pointing to. I don't need to pass the shared pointer in. Okay? I'm not operating on the shared pointer, I'm operating on the object on the other end of that pointer. Okay? So, and it should be possible to express that as an action form, right? I can consume P and return a new widget. Okay? That's a simple transformation. So objects used as arguments must be independent under mutation to uphold the law of exclusivity. They have to be. So we have to create our objects so they're independent. And copies are equal and logically disjoint. That's the number one way that you know that your objects are independent. Okay? There are three primary ways we can achieve independence. One is by disallowing mutation. That's the functional programming approach. Another is by disallowing sharing. Okay? And third is we can say, well, we'll only allow mutation when there's no sharing. So we'll take a copy on write approach. Okay? Now, extending independence with mutation, a mutable object may extend permission for mutation to its parts through projections. Okay, so if I've got a mutable whole, I can create a projection to it, and I can extend the privilege to modify that to the functions I'm calling through those projections. So long as those projections do not overlap. Now, a couple quick examples, right? Here's kind of the canonical structure that I use for a class. I've kind of moved away from saying you need a default constructor. A lot of times it just doesn't make sense. Let's just create objects with real values. If you have a meaningful default, that's fine. Okay. You've got some constructor that constructs it in terms of its parts. I've started marking my copy constructors as explicit. This comes from programming in Hilo. In Hilo, we have destructive move, and move is implicit. So if I say B equals A, then A is now gone and out of scope, and that was an implicit move. If I wanted a copy, I have to say A equals copy B. Okay? And that's even true of an integer. Okay? Which sounds like it would be very verbose. Turns out copies are actually rare, and this is completely fine. And so I've kind of started doing that in my C++ code. So that's for that. And then we want to have an equal equal, and luckily now we get a not equal by default as soon as we declare our equal equal. So this is the canonical template. Now you might have remote parts. Maybe you want them shared. That's fine if you're going to share things, no mutation. Right? That was our rule before. How do we get independence? No mutation. So now we've got a shared pointer to a const part. Now that's private inside of this class, and we're not going to expose that shared pointer outside of that class, because as soon as I do, I could apply a non-const pointer of the same type into that thing, and then all bets are lost. Okay? Now when I do that, I probably want to also provide equal equal in terms of the thing that my pointer is pointing to, and not the pointer itself. But it's actually not horrible if I just leave operator equal equal as default. It satisfies all my axioms. A copy is equal to a copy, okay? And if I expect my objects to be relatively unique, then that equivalence implies a true equivalence, just not the converse, okay? And that's okay. Your code will be fine. Okay. Or I could just say, I don't want to share it, I don't want to pay the overhead of a shared part, but I do have something that's variable size, or for whatever reason, I'm doing a pimple pattern. I want to make my part remote. So I can stick it in a unique pointer. That's fine. Okay? But you should still write a copy constructor that copies the thing that pointer points to. Okay? Let's make our type be a regular type. And now you have to define your own operator equal equal. Okay? If you just used the default operator equal equal, you just broke the axioms of copy, because copies will not be equal. Okay? So now you must. It's not okay to just default it. Okay, so we've covered whole parts relationships, and we've covered our functions in all of our arguments. And so now we have a way that we can build up larger things, okay? And they're independent, and so we can use them as arguments, and we're not going to create a mess. But code is never so simple. We have extrinsic relationships. Extrinsic relationships are any relationship that's not a whole part relationship, okay? It's an external relationship. And these things just happen. As soon as you have an object in a space, that object has a relationship with the space in which it resides. Okay? As soon as I have a vector of these parts, I have a whole bunch of relationships. A0 is before A1. Okay? Extrinsic relationships just happen. And this is where all of the complexity of our software comes in. Okay? We have to identify what are the essential relationships, and then we have to figure out how we're going to manage those relationships. And my recommendation is you take those essential relationships and you figure out how you package them into a class, and you make upholding those extrinsic relationships the invariant of your class. Okay? So they're only the relationships between the parts, and we're going to uphold them. Okay? So let's talk a little bit about relationships, because we're throwing that term out a lot here. A relationship is a connection between elements of two sets. For every relationship, there's a corresponding binary predicate, such as is married, right? I'm married to my wife. You can ask, are you married? I can say yes or no. A relationship between objects may be severed by modifying or destroying either of the objects in the relationship, okay? And that's really unfortunate. That's how we get spooky action at a distance. You modify something over here, and the pointer's invalidated over there. Okay? That's an example of invalidating a relationship by modifying just one end of it. Now, we can create objects that witness a relationship, right? When I said A0 is before A sub 1, there's no object there. Okay? But I can create an object like a pointer or an index or something like that, which is a witness to that relationship. Okay? It is not the relationship. It is just a witness to it. And so an object that is a witness to a severed relationship may itself be invalid. And it can be invalidated to the point like a pointer is a witness to a relationship, some relationship, where when that relationship is severed, my pointer is invalidated, and you can't even ask the question anymore, are you part of that relationship? Okay? That's UB. Okay? So that's a problem. So you have an extrinsic relationship if. Anybody want to cite some examples? Nobody? Did I lose everybody? We'll see. Your class stores a non-owning pointer or any pointer that doesn't witness the whole part relationship. You have an extrinsic relationship. Your class stores a key or an index. Okay? The functional programming guys will be like, well, we don't have pointers. I'm like, you still have relationships. Okay? You're still sticking them all over your objects. They're getting invalidated. You're not tracking them. I will bet my life that one of those failed software projects was written in a functional programming language. Okay? You reference a global variable. Okay? Global variable is shared. Pretty much by definition, you have an extrinsic relationship. You use any synchronization primitives, you have an extrinsic relationship, okay? By definition. If you didn't have sharing, you wouldn't need synchronization. Okay? So how do we reason locally about extrinsic relationships? We need to encapsulate them into a class, like I said before. We need to put this together. The relationships are maintained by that class. It's that class's job to manage the extrinsic relationships between its parts and make sure they are upheld. An intrusive relationship in a part, right, that would be like a pointer in a part, can only be modified by the whole that owns it, not by the part itself. Okay? Containers are an example of classes that manage extrinsic relationships between their parts. Right? Now, I wanted to put this up here as an analogy because I was looking for, like, can I find an example to kind of drive this home? And the reality is that once I start to develop a class that has some complex invariant, and I'm going to build it first as a bunch of separate classes and show that there's a relationship there, and then I'm going to package it all into a class and show that there's an invariant that needs to be encapsulated. So you're going to be looking at walls of code, and if I have to make it complex enough that it's meaningful, it's not a useful example. So I came up with this analogy. I'm not talking about the game of chess. I'm talking about this particular game of chess and this particular chessboard in this particular state. We only have 8 pieces that we're concerned with. Okay? Now, chess pieces, unlike my remote here, closer to my glass here, have no state. Okay? Does everybody believe me? A chess piece has no state? I mean, if I held up a chess piece, show me a moving part. Okay? Does anybody think a chess piece has a state?
Capture.
What's that?
Capture.
Capture. I mean, it has operations. Does it have a state?
King isn't allowed to have moved before it does the switch.
Yeah, so we get some rules around, did a castling happen? Could we en passant, right, has a pawn moved yet? Things of that nature. But we're talking about this chessboard, okay? So too late. If there was castling, it already happened. We can't en passant. None of our pawns are on square one, okay? Okay, so maybe you could model those. You might say color, but that's known at compile time, right? Okay. So none of these have state. Somebody over here?
Piece can be captured or not captured. Right?
A piece can be captured or not captured. Is that part of the state of it, or is that an extrinsic relationship to the part? I don't know. If I held up a chess piece, tell me whether or not the chess piece was captured.
The king could be checked or not checked.
The king could be checked or not checked. Again, relationship. Okay? Relationship specifically between the king and some other piece. Okay? So there's no states in chess pieces. Okay? What I thought somebody would say was position, right? But just like an object in memory, right? It's not the memory location that's the state of that object. I can create an empty object with no state at some particular position. It's not the state of the object. That's a relationship between the object and the container that contains it. In this case, there's a relationship between all of these pieces and the board that contains them. Okay? So here we have 4 kinds of chess pieces. They all have a really well-defined contract. I'm not going to go through it, but your kings, you can pick one of 8 directions that they could move in. They only move 1 square. Your queens can move in the same one of 8 directions, but you get a count of n, which is between 0 and 7 for spaces that they could move. Our knights could move in 8 places. And our pawns are a little bit different. They can only move 1 space forward unless they're capturing, and then they can move at a diagonal. But we could write those functions. All very well-defined contracts, all very simple. Okay. And our chessboard is only 8 by 8. We only have 64 squares. Okay. They all contain a variant of either nothing or one of our 4 types of pieces. Even if we separate them out by colors, we only have 7. Okay? But yet we created a super complex system here, one that's very difficult to reason about. You don't need many objects and many relationships within your system before your ability to reason breaks down. Okay? So if I start to ask, well, I've got the goal of winning the game and it's white's next move, that's a complicated system. Okay? If I say, well, the goal is I need the queen in the top right corner and the king in the bottom left corner without either of them getting captured. Okay? That's a complex thing to go and reason about. And we build these little systems with our code all the time. When I came up with this example, I was like, is there a smaller example? What's the smallest example I could come up with for kind of number of objects and number of relationships where reasoning gets hard or breaks down entirely? And Dave Abrahams on my team said, oh, I've got one. This one. Anybody know what this is? This is the 3-body problem. Okay, very popular these days because of Netflix. So what's the problem here? We start with 3 bodies. They all have very well-defined contracts. They all have a relationship to each other. They all start with some initial conditions. And now, once you set this into motion, you can't predict at some given state n where these 3 objects are going to be. This is where the chaos theory originates. Okay? There is no closed-form solution to where all of these objects are going to end up in space. And you don't need 3 objects before you get chaos. Okay? I've got this other example here. So this is a Henan map or a Henan map. I'm not quite sure how to pronounce it. This is just 2 relationships, and it forms this chaotic system. And it's impossible to predict where it's going to go. It's 2 relatively simple formulas. Now, how many people here have been in a situation where they've been assigned a bug, and the customer says, or whoever, QE or somebody said, okay, well, what I did was I did step A, and then I did step B, and then it crashed. And you do step A, and you do step B, and it doesn't crash. Anybody hit those? Do you kind of see where I'm going? How do you know, given step A and given step B, whether or not the system is going to crash? Maybe there's a whole bunch of other state that you're relying on. There were things that happened before A, or things that happened between A and B that the person forgot to mention. Okay? And so given that small amount of information, we're not able to predict what the next step in the system is. We just built a chaotic system. Okay? We're not able to project forward. We need to be able to figure out where we are. We need to go all the way back to the beginning and take every single step exactly as it was to get to where we end up to be. Okay? It's not enough to just get the tail end of that sequence. So what we want to do is try to build systems that are not chaotic, where we can predict the next step just knowing the previous state. That's it. Not everything around it, but of that one object of the next step. If you said, I crashed inside of this function, it's like, just give me the previous state of the arguments to that function. That's all I need to know. Should be all you need to know, but we don't build systems like that. Okay? So what kind of structures are good? Hierarchies are good structures to have in code. This is the whole part relationship, right? Those form containment hierarchies. Hierarchies are good structures, relatively to reason about. If you have them that exist outside of a class, I don't recommend it, but try to build a structure that somehow enforces that stays a hierarchy. You don't know how many times I've seen somebody take like a view system and they say, oh, I took this shared pointer from this view over here, and I put it over here in my view, and they both had parent links, and that parent link overwrite that parent link, okay? And now my system did something bizarre and wacky, or crashed, or when this thing moved, that thing moved instead, okay? How many people have seen problems like that? Yeah, quite a few. Okay, so if you're gonna have extrinsic relationships and you're not gonna manage them inside of a class, please do, but if you must, have some facility to make sure it stays a correct hierarchy. So what's the next thing? It's a polytree. Who knows what a polytree is? One person? It's like not quite a generalized DAG. So a polytree is a little more than a hierarchy in that I can have joins, but I can't ever rejoin. I can't branch out and come together. Okay. Now, this is a little more dangerous to have as a structure, and I need to take more care if my objects are forming a polytree in how I manage this. Every join is a potential contradiction. Every join is where your race conditions happen. Every join is where you violate the law of exclusivity. Every join is where you write the value 1 from one function and you write the value 3 from the other function, and you're like, why isn't it 1 anymore? What happened? Okay? So almost every join we write in our code, we write it as last one in wins, and that's almost always the wrong rule, okay? So think about your joins. Now, joins aren't bad, right? Addition is a join. I can add 2 numbers and I get a result, but when I add 2 numbers, I don't say throw away the first one, just take the second one, okay? Okay, so if you have a join, make it explicit and specify what the semantics of that join are. The next thing we have is structural complexity for DAGs, okay? So DAGs now, directed acyclic graphs. I'm losing people. I'm over time, aren't I? I'm way over time. I will try to speed it up. Sorry, guys. So structural complexity of DAGs. Here, what you've got problems is inconsistencies, okay? I fan out along one way, and then I come back in, and those are two relationships that represent different aspects of the same thing, and are they consistent? And when I wrote that code, maybe they were consistent, and then somebody modified the relationship over here, but forgot about that relationship, and now they're inconsistent, okay? So more dangerous. And then if we get to the place where we've got a fully directed graph, we've got a loop, now reasoning about this is pretty much off the table. So what you need to do at this point is identify where that loop is, figure out how to structure that as an algorithm, what are the rules, when does this terminate, right? What governs this, does it converge, and make it one node that represents that entire loop. And this leads us to the end of free relationships, right? So we started talking about small talk and object-oriented programming and this dream that we could just build networks of objects and connect them together and everything would live harmoniously, right? It would just all work, but it doesn't, unfortunately. You know, I think the 80s programmers were the hippies of the 60s and 70s, right? They were fans of these free relationships. Okay. So a free relationship is an extrinsic relationship that is not managed between parts of an object. Okay, not managed at all. If we assume local reasoning, what meaningful structures can we build with free relationships? Is there anything? It's an interesting problem. If I want to have a global variable and I want it to be shared, what meaningful thing can I do in that global variable? Is it never okay, or is it sometimes okay? And how do you qualify when sometimes is? Okay. Well, this is the question that's asked in this paper. What is the family of problems that can be consistently computed in a distributed fashion without coordination, and what problems lie outside that family? How do we know? This paper is from 2019, so this is relatively recent work. And they have an answer and a proof. It's a very nice paper. A program has consistent coordination-free distributed implementation if and only if it is monotonic. Anybody have any feeling for what that is? So you know what a monotonic function is, right? So, right, a monotonic function like never comes back down. It goes up, right, or it goes down, right, but it never goes up and then down. Okay, and what does that mean from programming? Well, conflict-free replicated data types, CRDTs, if you've heard about that, that's an example of a monotonic system. And it provides a framework for doing monotonic programming patterns. Immutable variables are a very simple example of something that's monotonic. They don't exist, and then they come into existence, okay, and then they never go out of existence again, okay? So that's another example. In one of my talks, I gave this example, which is, I refer to it as the Russian code check algorithm, which is kind of a cute play on Russian peasant algorithm, and I came up with this because I was actually watching how a woman was very efficiently managing codes at a code check at just blazing speed. It's like, how does she do that? Well, here's the trick. She's giving out tickets, the 0, 1, 2, 3, 4, which are always increasing in value. And when people come in and hand them her ticket, she can do a quick binary search on the rack and pull out their coat and hand it to them, okay? And then when the coat rack is filled up, she just squishes it all together and keeps putting the new coats on the end. New coats always go on the end. Numbers are always increasing. So we can stack things out this way. We put in coats A, B, C, D, E, F, G, H. And then people come in and claim their coats, and so now their coats are gone, so we tombstone them. And then the rack fills up, so we just push the remaining coats back together. And then more people add more coats, now 8 and 9, and we keep going. This is a monotonic system because the system will never repeat its previous state, okay? It will never go back to the state it was in before. which means that I can safely share my code tickets across threads. I can distribute them out, and my system is still meaningful. You can either get the coat with the ticket or not get the coat with the ticket, but you'll never run into an ABA problem in threading. Okay? Everything is well-defined. It's monotonic. It's consistent. Okay? So if you want to build those free networks, you have to build monotonic systems. So in summary, be conservative when you're writing your code, okay? When you're calling a function and it doesn't have a well-defined specification, assume that anything that doesn't appear to be well-defined is an implicit precondition that failed to be documented. Don't assume you're going to get an error back, okay? Avoid modifying shared state. If you don't know it's shared, consider it immutable, okay, or make a copy. Avoid creating new sharing. Don't hold a member by a shared reference if you didn't create it. Just don't. If you're dealing with reference semantics, make it clear if you are returning a new object or a reference to an existing one. And don't take shared pointers in your interface as arguments, okay? And remember the power of preconditions to push the responsibility onto the caller. It seems like a silly thing, but you do that and the responsibilities become clear. And you're actually doing your caller a favor, because now your caller doesn't have to reason about all these other cases. They just have to assure that they're satisfying your preconditions based off their arguments and their preconditions, and everything flows down. Interfaces should make the scope of the operation clear. Projections provide an efficient way to achieve value semantics and still manipulate the parts and still have mutation. It's the client's responsibility to uphold the law of exclusivity. Okay? The implementer cannot. Okay? Don't pass projections that overlap a mutable projection. Implementers provide types with value semantics. When you're writing a new type, don't create shared types, right? Uphold value semantics. Make sure that your equal is the right thing. Make sure you implement copy. Confine extrinsic relationships between parts within a class and write down the class invariants and check your class invariants and write test cases for them. As the relationships between parts scale, seek a more general solution. And this last point, when we looked at the chessboard with 8 pieces, if you're looking at that chessboard and you've got 8 objects in your code and you've got the small address space and you're trying to figure out, okay, you're writing code that's like, if the black piece moves here, then I'll move this piece over here, but if they do that, then I'll do this, and you're getting this whole morass of logic, and there's no way you can reason through all the steps. And then you're like, oh, well, then next, if they had moved there, then I have to consider this case. Okay? Then you have to step back and say, what's the algorithm to play the game of chess? And how do I write that? And at some point, your individual relationships become so complex that that's your only solution. You cannot reason through all the possibilities. You have to stand back and solve the system as a whole, and then implement that algorithm, and now your chessboard's okay. Okay, so that's the end of my talk. I apologize for running over time. I hope you all enjoyed it. I am here the rest of the day if anybody wants to chat or go out to dinner or whatever, since we don't have time for Q&A, but if anybody wants to come on up, please feel free.